My name is Irene Piatek. I work at the Johnson Space Center, and from 2003 to 2005, I was the Systems Engineering and Integration Manager for the Orbiter Boom Sensor System as part of the Return to Flight program. Because of the nature of the accident where pieces of foam had hit the reinforced carbon-carbon wing leading edge area, there was a need to be able to inspect that part of the orbiter so that we could see if any damage had taken place, because there was no other way of doing it, and even the arm couldn't reach it all by itself. So there, during the summertime after the accident, there was a small group that put together basically a concept of operations that said if we could add another 50-foot extension onto the end of the arm, it looks like with the robotic analysis we were able to do that we could actually see or be able to manipulate something at the end of that boom so we could inspect those areas, because otherwise there was no engineering way of detecting anything. There were no sensors in that area of any kind. There was no visual capability. We didn't have a God's eye view camera, if you will, available to us. So the study team came up with this concept of adding this extension onto the end of the arm so we could actually be able to, like, take a camera out and do an inspection to ensure that if foam had popped off the tank or ice or any other kind of debris hit those sensitive areas, and we'd be able to detect it and be able to do some kind of either immediate return or continue on to the space station, do some kind of rescue mission, or whatever was the right course of action at that time. So we knew we had to have some kind of a boom extension, and McDonald Detweiler Associates up in Canada had spare parts for another robotic arm. So that was immediately available. We wanted to see what kind of hardware inventory was available to us as an agency, because we knew there was a criticality from a time standpoint relative to flying again. Sandia National Laboratories had flown as an experiment this laser dynamic ranging instrument, LDRI, and NepTec, another Canadian company, had this laser camera system that also was in an early flight experimentation kind of phase. So we knew that what their capabilities were. We knew we could put them on the end of the boom. We were also looking at very early what kind of maybe high-definition camera to put on, and that was actually added later after the first return-to-flight mission. But so we had these pieces together, and then it was a matter of getting the right contracts in place, the right agreements in place. How are we going? How are we going to put all those together? And we knew that the orbiter itself had actually at one time been outfitted so that the other side of the vehicle would have a second robotic arm. So that infrastructure was already in place to be able to do that attachment. So we had all the elements available. Then it was just a matter of putting together the plan as to how these things were going to all play together and how the companies were going to work together and how we were going to actually install it on the vehicle and continue on with the project. So. The requirement to detect, as we knew it at the time we wrote the requirements document in September of 2003, was 1/4 of an inch. This was based on testing that was going on in, 1/4 of an inch is about yay big, in San Antonio, based on the shooting foam and ice and other kinds of debris at this reinforced carbon-carbon panels. And by keeping in touch with the testing team, we began to realize that over time that this requirement was changing, and we didn't know what it was going to settle out at. So we were doing these development efforts in parallel as what was going on. They were doing the testing, and we were trying to build up the system with the boom and sensors in order to achieve what we needed to do. And ultimately, the real requirement was 20 thousandths. And we did engineering testing on our sensors and the boom and with motion to establish what the capabilities of the sensors were, and it just so happened that the capability of the sensors matched up with the ultimate requirement that we needed to have. So the project team was initiated between the orbiter project manager and the engineering director, and they determined the top key players. The project manager would be in the orbiter project office, and the SE&I lead would be from the engineering directorate. And then they selected the personnel to do that, and I was chosen to be the SE&I manager for that team. So my first job was to establish how we were going to operate this team, what tasks and what products that we were going to be responsible for as the engineering directorate and SE&I team. And those were the requirements, the schedule, the integrated electrical analysis, because it crossed too many boundaries for other than an SE&I team to be done, and how we were going to basically operate. So once we got those top 2 or 3 people named and identified, the first thing we did was start talking to the companies and corporations that we knew were going to be involved in establishing those contractual relationships. And we decided to have basically a weekly meeting with the key people from each one of those teams to discuss the schedule. So we used basically our schedule, this integrated master schedule, as the basis for establishing that communication, making sure everybody was all synchronized with all of our tasks, and we kept that updated on a very regular basis. When we started, it was only maybe 40 or 50 lines long, but by the time we got done, it was over 400 to include all the activities we needed to do, basically from the beginning with having the requirements review in October to actually flying it in July of 2005. A related risk in all of this was if we kept delaying getting the shuttle back to flying status again, we were going to impact the resupply to space station, being able to carry food and clothing and other consumables up to space station to keep our crew alive up there. But there was also the need to continue building out the space station. We had not flown at that time several major elements that only the orbiter could fly to the space station to continue its build out. Here's a few things that we did to make this project executable. One of the things we immediately did was we had a system requirements review in October of 2003 that immediately got the entire team that we were working with on the same page with regards to what the ultimate goal was. It helped to establish the schedule that we were going to have to work to. It gave us evidence to go to the program manager, the shuttle program manager, to say, no, we're not going to be able to fly in March because we just can't pull all these pieces together in time. So we were the first ones to say that we're going to need a schedule extension. And as we moved through things, we began to realize there were decisions that had to be made that were schedule-driven rather than taking the time to look at alternatives. For the boom in particular, I mentioned we ultimately used segments available from the robotic arm. We also did a very short trade study to look at a triangular truss for the boom, but we dropped it fairly early on because we didn't have enough time to go in and do an extensive trade study on that. And again, it was schedule-driven, so we made those kinds of decisions as we had to. Were they optimized? It's hard to tell at this point. It's hindsight being what it is. So we made those decisions very consciously, very deliberately, knowing that we had to be successful. We had to do it within a very short order time frame because we knew that the vehicle wasn't going to fly again until we had this inspection capability. So by using the schedule, by keeping everybody on track with requirements, having intermediate design reviews at the various elements like the sensor folks, the boom providers, the Boeing people who were providing some other elements to this activity to install it into the vehicle, and involving everybody from the Kennedy Space Center to our safety guys, the crew. We were able to keep everybody on track, and we were very highly motivated because we wanted to fly again. We wanted to be successful and get back into space. So when we started, we didn't realize that it was going to be a full-up systems development for some of these components. We were pretty much, because of schedule, going to use the components, particularly the LDRI and the LCS, basically as is. Maybe do some modifications to address maybe some thermal issues, that kind of thing, but basically use those as is. And as we went through the preliminary design reviews and critical design reviews, we began to realize that wasn't quite possible. So we ended up making a number of changes to mature the technology a little bit, to make it more robust, to make it feasible, to be able to do the detection that we needed for this capability. A couple of things we encountered along the way, even though we thought this would be a relatively simple project because we were using existing components and incorporating into an existing vehicle. Two things we found almost immediately were that by having this stiff pencil-like object on the side of an orbiter that bends under thermal conditions on orbit, there was loads and stresses put into the vehicle that were causing things to break. So we had to overcome that by analysis, and we figured out, yes, eventually we could do this. A second issue was we had over 100 feet of wiring that we had to take into account in order to have these sensors operate at the end of the boom. And we had to redesign our electrical distribution system to be able to accommodate the two sensors so that they both had the right voltage in order to operate and to be able to have this capability to inspect the vehicle as we went through flight. We've gone into this project thinking that it was relatively straightforward, that we weren't going to necessarily encounter what we call showstopper kinds of issues, and ultimately we did. And I think the lesson that we learned from that is that by having the key analyses done early enough in the project and the people making management aware of what was going on, we were able to address these problems early on in order to achieve success for the project. We knew early on that the 1/4 of an inch requirement was probably not the right one, that it was going to be smaller. So as we went through the development and maturing these sensors, the LDRI and the LCS, we kept testing and analyzing and trying to establish what their real capabilities were. We even went so far as to take the LDRI team from Sandia National Laboratories down to KSC for a day, and they brought their sensor with them and were able to get within touching distance of the RCC on a couple of the orbiters that were in the orbiter processing facilities. And they were able to capture data and understand what the surface textures were of the RCC, because it's not a smooth surface. It's not the same coloration. It's got ripples, it's got gaps, it's got dings and dents. And by doing this testing and doing this analysis, we were able to establish fairly early on what the capabilities were. So by keeping in touch with the testing team at Sandia, who were shooting all this stuff at foam and at tile, we were actually able to start converging the requirements and capabilities of the sensors with what we were seeing from the testing teams as to how the RCC was impacted and what kind of damage we were going to have to be able to detect. The key lesson is keeping in constant communication and coordination with these various teams and being able to establish that you needed to do the testing and that you were able to justify it from a technical standpoint, and getting your management team behind you to be able to go off and do that. Return to flight was all about getting the orbiter back into space again. I mentioned earlier about the need for ISS resupply and keeping the build of the space station going. So we were under constant schedule pressure, and the schedule kept moving depending on which system was having difficulties at the time, because there were multiple activities on multiple fronts getting the return to flight, and we were one of them. We were one of the key ones. But because the schedule kept moving, we had to make decisions, and then that was it. We made that decision. We moved on. We kept going forward. We never went back and revisited decisions, especially the key critical ones that were going to cause the schedule issues. So we were constantly moving forward, and in that decision space, with the trades were looked at very briefly, and a decision was made, and again, we moved forward. We had what we called heritage hardware. We had these boom segments. We had these sensors that had flown, but they were probably at a technology readiness level of about a 6. So we knew what they might be able to do. But trying to put all these elements together was really very challenging, because they were off the shelf, but by the time you tried to put them all together, you had something brand new that was hopefully workable, and we had a number of things we had to do to mature this technology and mature the integration of these systems so that they could work together and could be integrated in the vehicle to achieve the goal of being able to inspect the RCC. So we had a number of organizations involved in this activity. We had Boeing from California. We had, as I mentioned before, MDA from Canada, NepTec from Canada, Sandia National Laboratories. We had the folks from Kennedy Space Center who was going put everything into the vehicle, and trying to keep all these elements, plus all the folks in Houston, trying to keep all these elements tied together was a real challenge. And of course, we're spread out all over the continent. So communication was key. I mentioned before that we had this weekly systems integration meeting. There were also discussions offline going on all the time between the various elements. And we really focused on dependencies and deliverables in this weekly meeting. We talked every week about, okay, Boeing, you need this information from Canada, or MDA, can you provide this? Yes, I can provide it by this point in time. We put that in the schedule, and we tracked it. And that was the key communication element that we had. And if we hadn't done that, there was a real significant possibility that people would have been going off in all different directions, and we would never have achieved what we did within the time frame that we achieved it. The key lesson here was for us to just keep talking together, working through the issues, constant communication, and understanding what the ultimate goal was. And that we were all empowered and enabled to actually go off and do it this way. One of the things that we had to work through early on was that the hardware we were talking about, in the combination between the orbiter as it existed and the hardware as it existed that we were using, this heritage hardware I've spoken about, is that they were built to different safety requirements with respect to reliability and redundancy. And we're trying to mesh all of these things together to operate this system from a safety perspective of the highest criticality, which means that if it didn't work, that we wouldn't kill the crew or damage the vehicle in a catastrophic fashion. We recognized that early on, and we kept working with the safety community to work through these issues and make sure that by the time we reached our certification standpoint, that we could be certified and have this hardware be flown on the vehicle and used in the manner that we wanted it to be used. The key lesson there was, again, identifying the problem early on and not letting it languish, but going in and attacking it and having the discussions and getting the agreements done so that we could proceed without having to make major changes to the orbiter or major changes to the hardware to achieve this critical stature or requirement for the overall system functionality. When we talk about team composition, basically people were assigned to the team from their various organizations. And what is important from a team functionality standpoint is that we have the necessary experience in some individuals in order to be able to achieve it. So you might have some people with a little bit less experience in some areas, but there would be someone who had that requisite experience and could help move the project along and keeping the team functioning as it needed to in order to overcome or deal with the schedule pressure, the time constraints, the technical challenges that we had. So if you looked at it from an overall team perspective, we did have the right levels of experience in the right places at the right time to keep the project moving forward and getting the things done that we needed to get done. When you're put on a project team, you don't always get to choose your project team members. But I think the key lesson here that we had in order to keep the team moving forward was the fact that we were all very highly motivated. There were a lot of significant challenges in this project, the environment in which we were working, the schedule pressures, the technical challenges. But despite the difference in experience levels that we had and the backgrounds that we brought to the table, the motivation of the team was to recover from this accident, to get the orbiter flying again. We were all personally invested and motivated to get this job done, to get us flying again, and to recover, frankly, from the accident that had taken place. And for some of us, it was the second one that we had experienced. I had a couple of key takeaways from working on this project, and one was getting the team focused and moving all in the same direction very early on, and we did that by having the system requirements review almost immediately. The second thing was keeping track of the deliverables and dependencies and the constant communication, and the vehicle that we did that with was this integrated master schedule. And by having that in there, by discussing it weekly, keeping everybody focused, really enabled the success of this team. If you have any questions about this project, the Orbiter Boom Sensor System, please feel free to contact me at the Johnson Space Center through the Engineering Directorate. We'll be more than happy to answer your questions.
Perfect.
This is the NepTec laser camera system that we flew and operated for the first time on the second return-to-flight mission, STS-121. So the first thing I want to show you is that this down here, this mirror area, is the business end where the lasers actually emanate and we receive the data. This shiny or large area up here is actually a radiator because these boxes produce a lot of heat, and we have to be able to conduct that heat outside of the box so that it doesn't fry itself internally. So we have very large radiative surfaces to be able to do that. This box is actually quite heavy. The piece that it's standing on is actually a bracket for a high-definition digital camera that we also used on later flights. There's connectors up here that you probably can't see in the video, but this is where your power comes in and your data and commands come in and go out. This unit in particular was used for what we call focus inspection. The first thing we did on any given mission was we used the LDRI to scan and to look for any potential areas of damage. And the analysis team would then go in and look at those scans and see if they needed to do what we call these focus inspections. Then this unit, with its camera, the digital camera, would be used to go in and focus on these smaller areas to see if there was any damage based on the initial assessment. Now, fortunately, through the rest of the life of the orbiter, we never found any damage once we started looking at it from a focused inspection standpoint, so we were able to clear the vehicle every time for landing.